Okay, so this is a revelation that I had over Cell Theo, and I'm going to break down the significance of it and just how precise and accurate this method of occlusion measurement is, and what it truly means to test an internally consistent coordinate system using external references, i.e., the physical intersection of occlusions, because the only thing that's going to occlude light is the physical geometric intersection between the source and a physical object. So we start with a simple rise over run to a peak. So we have a distance and we have an elevation. That gives us an angle. So the flat Earth, in this case for Pike's Peak, predicts 231. Now on a globe, how you derive distance is based off of central angle theorem. And what that means is you can think of a circle with a slice of pie cut out of it, and that angle of that pie slice is going to be the distance. So, in other words, the 50-kilometer distance to the mountain peak from the observer is 27 minutes of arc on a globe. And the way that they say the stars move and drop angularly is due to 60 nautical miles per degree following an Earth of a radius of 6,371,000 meters. So this is what merges the celestial and terrestrial spheres together, two conceptual models to give ground positions of stars on the ground relative to a fictitious observer at the center of this. So this is what creates the 15 degree per hour position for a star to be relative to when you see the apparent position. So this is what creates the ground position representation in their coordinate system. So a ground position exists as a calculation within the coordinate system relative to this fictitious observer setting a star moving at 15 degrees per hour. So this is a internally consistent coordinate system because you're always going to be referencing the symmetry of that system from your fictitious observer. And then anything you see, you can relate the ground position to where it would hypothetically be in your conceptual model. This is significant because what Mike did is he came up with a method of measuring occlusions based off of the elevation differences of what we predict. Because on the globe, as the star gets lower angularly because the Earth is rotating at 15 degrees per hour, it's going to drop by 27 arc minutes over 2 minutes and or yeah, 27 arc minutes angularly over 2 minutes and 29 seconds in reality, in real seconds. And as it approaches 13 arc minutes in angular difference from where it once started from the observer, at which takes 1 minute and 15 seconds, it's going to be at 2 degrees and 19 arc minutes angularly in the sky for the observer. And this is speaking about the true position, which is what the coordinate system is going to use to explain where the optical apparent position is. And with corrections here, with this astronomical refraction correction to explain the difference between apparent position and true position, this is what is binding uh, the GP of the star to the coordinate system to make it relative to that fictitious observer to give this meaning. So when the star drops this much, it's about 2 arc minutes off of the geometric intersection of what the globe predicts for the relative mountain elevation based off of rise over run minus drop over distance. So if you do rise over run to any peak and then subtract the half central angle here, which you can get from 180 times the distance over 2 pi r, which just converts the half central angle into from radians into decimal degrees, and then you can convert that into an angle. And whatever that angle is going to be the drop over distance. You can do a tangent function to convert that into what it would be in relative meters over that distance. So you can look at it like that. So anyway, whatever the geometric alignment for that peak is, and in this case for Pike's Peak, there should be 201 meters of drop over distance, which corresponds to an angle. If we subtract that 13 arc minutes from the rise over run to the peak, we get 217. That's what the globe geometrically predicts. So when the star is at, when the time is 1842.04, which is about 1 minute and 3 seconds before the occlusion, the star is geometrically aligned with the peak at 217. So this is where the occlusion should happen. So this number 27 here, this should not, this should be intersected by uh, about 17 arc minutes. So it shouldn't be able to traverse the full amount. This is when the occlusion should happen for the globe. Now, on a flat Earth, if the Earth is flat and the elevation of the star isn't actually changing the true position, what we're considering the light source in both models using the celestial sphere, if that elevation isn't actually changing, then it's gonna swoop right on by that full central angle. It's gonna complete that full angular drop, and at the end of that drop, there's a mountain peak, because remember, the distance to the observer is also 27 arc minutes. So the angular drop over that distance, over that time of 2 minutes 29 seconds, is now going to be angularly aligned with a mountain peak. There's a mountain peak there with a rise over run of 2 degrees and 31 arc minutes. And that's when the star gets occluded every time. When the star is geometrically aligned with the actual, or with this, when the star in reality, the star's true position is geometrically aligned with the mountain peak. And that would only be possible if the Earth was flat, because the intersection would have already occurred on the globe and they wouldn't have the full central angle. It wouldn't be able to fully drop. So if you take the star's true position at the peak and subtract that from the observer's true position, and this is referencing, their coordinate system internally, you get this number right here, which is 0.45 decimal degrees, which converts into 27 arc minutes, which is the central, the full central angle drop in that angle. You could call it. You could look at it like, you could, what we call it, the celestial drop, because that's what it's going to be over the full distance. But that full distance also corresponds. I'm sorry, but that angle also corresponds to the distance between the observer and the peak. So, with that
Question. That's
said,
cool.
what's that? Yeah, 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 absolutely.
Yeah. So okay. So when you say the celestial drop 360, that's the full path, the arc length path.
Yeah, so that's the full amount of drop over that arc length. So, like, if you were to put a time to say, hey, how long is it going to take to drop 27 arc minutes relative to my position? Because during that, there's going to be an intersection with a mountain peak. Because that's how we get the time for how long it's going to take for that star to hit the mountain peak. So
So
if
like
you were,
regardless of if there was a mountain peak there or not, what you're doing is the distance between the arc length distance between the observer and the mountain peak, no matter what, is going to be that.
yes,
Got it. And then you're confirming it with the occlusion of the star by the mountain peak, saying, okay, this is when it was actually occluded at.
yes, because they would have to say that the elevation of the peak or the elevation of the observer is incorrect, because the only thing that would actually cause an occlusion, it, while referencing their coordinate system internally, which is, if you're not familiar with how meters are a ratio of a terrestrial meridian and how all that works in terms of a conversion of a nautical mile, which is just a ratio of a circle and all of that. So they've pretty, and then having sea level defined, how they have it with the ellipsoid and all that, uh, within their coordinate system, there exists a mountain that has a relative elevation of 2 degrees and 31 arc minutes, assuming no drop over distance, and that's what, and that's at the end of this arc length here. That's at the end of that distance there. And so the only thing that could cause that occlusion in their coordinate system is a mountain with a rise over run of 231, because that's the only thing that's there to occlude it now. And
I got you.
and
Okay.
so the difference
Which is
here,
why it needs to occlude earlier.
correct, correct. And the angular difference here between, so now if we reference the true position of the star, in their coordinate system to the mountain peak, there's a 2 arc minute angular difference. And that angular difference is because the coordinate system is fictitious and the star isn't really angularly dropping. If it
In
were,
reality, right?
yeah, if it were, then at the time of occlusion, we wouldn't be able to derive the full 27 arc minutes here. It would be plus or minus some. So like you know how they say, oh, refraction, this or that. None of that. There's no variance in the every single time it traverses the full central angle. So Mike's like how we've been presenting it about intersections being geometric, and once the light source is occluded, there's no the refracted, none of that matters, right? We're spot on, but with that assumption and working, because when we look back at the occlusions and the difference in their coordinate systems at the time of occlusion, we get the full central angle.
Hmm. One more question.
Yes.
So, in
Oh,
response, in terms of account,
hold on, real
oh,
quick, real
sorry.
quick. So they take the zenith measurement of a star, map it to 15 degrees per hour. Now, in both models, the star's true position is moving at 15 degrees per hour relative to an observer. That's what's true.
That's just reality. Yeah.
That's reality. What's not reality is the angular drop of that true position relative to the observer. That is completely mandated by their fictitious coordinate system to give it that relative ground position in their coordinate system. And so the difference here, uh, in this intersection, is their coordinate system in reference to reality, which would be the rise over run to the peak at the end of this arc length.
Right. So that was going to be my counter question. So, could they claim that the arc length isn't actually from the observer to the mountain peak, but from the observer to the horizon? And then they would say like, no, when the star actually physically gets obstructed is by the horizon, and then because you should, so like, okay, could they say that it refracts beyond that arc length from the observer to the mountain peak, where they say, well, the star is actually already occluded, it's just being refracted up, and then our central angle is actually okay. Could they actually use that as a rescue device?
No, because they have a specific amount of refraction here to bind it to the true position to give it relevance to their coordinate system. And the way they interpret refraction for the celestial bodies is anytime you see a celestial body, they say,
There's a
uh,
certain coefficient of refraction
there's
that's
a certain amount of
associated with it.
refraction. And then in celestial navigation in particular, which is the backbone of latitude and longitude, and giving merging the celestial and terrestrial sphere to give ground positions to stars, meaning like that, this number has to be physically whatever it is, and it has to compensate 1 to 1 for any sort of curvature or whatever. But as everyone correctly noted uh, yesterday during the Celtheo update, is that the stars occlude instantaneously. They don't linger into the mountain or hover above them above the mountain, the way they say that the sun's true position is geometrically below the horizon, but it's being refracted up and all that. That's they need to invoke that amount 1 to 1 to explain literally everything. So at the time of occlusion, they predict to be geometrically, like the light source, or the apparent position, as they would say, due to refraction, is geometrically over the peak by 1 arc minute. So they would need 7 more seconds to have an occlusion. So this would, if there was a 7 second difference at the time of occlusion based off of that, that would actually be
It's
good
28 arc
evidence.
minutes.
That would be good evidence for their refraction hypothesis. But they don't. But again, they don't get the full central angle. Only flat Earth gets the full central angle. So
Right. Oh, dude, I see what you're saying.
yeah.
Okay.
So either way, when I say, when I was calling them out last night, saying, you're just cutting off your refraction arbitrarily to say that it matches flat Earth, because at the end of this arc length, there's nothing else to occlude it. There's either a flat Earth prediction mountain, or there was the once was, or there's the once was globe prediction at an earlier time, for their relative angle at their intersection.
Right. It has to be earlier because in their conception, Earth is rotating away, or it's rotating,
Well, yeah,
causing the
it's
declination of the star in their
right.
conception, but it's not actually declining. It's not actually declining. Oh, wow. Okay. I see what you're saying.
Yeah. And then so to kind of look at this diagram here, when I was
Oh,
talking about the central angle and all that for their conceptual models. So this would be the terrestrial sphere, and then above would be, the celestial sphere. But to actually use them, you have to bring the celestial sphere down to here via a geocentric
fictitious
transformation,
observer.
which is the
Yeah.
fictitious observer that's going to bind the angular drop of a star to the arc length of this right
Oh,
here,
I see what you're
right here.
saying.
So now when they have the observer on the ground, now in this case he's a little above sea level or whatever, so he's right here. But in this case, that's what's going to create the central angle for him to the peak. And then when we look in stellarium at 2 minutes and 29 seconds before the where the true position was before the time of occlusion, before it angularly dropped 27 arc minutes to intersect with the peak here. Um, uh, when we go back and look at that time, the angle for the observer, that true position, is 2 degrees and 33 arc minutes. So once on a globe, this peak would be lower, but the elevation angle of the star is changing based on the geometry of Earth, following the 69 nautical miles per degree, which is what this whole central angle thing is based off of in relating to the fictitious observer to the celestial sphere for this to be useful. So their geometric intersection occurs at that earlier time. It occurs at 1842.04 for the observer, because they're basing it off of the relevance of the 15 degree per hour true position to give relevance to a ground position,
Correct.
based on that angular change. So that's
The
it's absolute.
apparent position is really only used for celestial navigation, and that's when you would incorporate the refraction, the celestial refraction based off of whatever angle that is. So there's a specific coefficient that's added in, or that's used based off of whatever angle it is, and they use like what they use like series, like a expansion series, depending on like, oh, it's at this angle, this is how much refraction, give or take, should be right here incorporated based off of whatever refraction formula. But what you're saying is that once it gets past a certain point, right, in terms of elevation, so for in this instance, the mountain peak is at 233. So regardless if the true position of the star goes beyond that, it needs to be occluded in their model. For us, we can have it linger a little longer because we don't have it going beneath our feet. I got you. I
Yes.
don't know if I still meant that properly,
Yeah.
but I kind of get it.
Oh,
Pretty
the
good.
way you just said that made so much sense.
Got you.
Yes. So the angular difference here is only in separation to their fictitious coordinate system. The If this distance were meaningful, then it would have shown up in the central angle difference between observer position and true position of the peak and observer there. But it didn't. But it did. And by traversing that full angular distance to the peak, that's when it got occluded. So let's see, where's that diagram at?
So that's their entailment. What you're showing right there on the screen, that is the entailment based off of their central angle. If they're using a fictitious observer at the center of the Earth, you know, extending it outward toward the celestial sphere, and then that central angle remains fixed because the stars remain fixed in their conception, and it's actually the Earth rotating that's causing the declination, then that central angle cannot change willy nilly.
Correct.
Oh, dude, that makes so much sense. Oh, they're screwed.
Dude, it's so bad. Like, yeah, when you actually get the like
I mean,
how
I'm
they're
kind of
the backbone of their
digesting it.
thing, it's so bad because the only thing that exists here in between this in reality, the meters and all that is all relative to their conversion and ratios, so it's all internally consistent. So whatever the distance is, could be stadia, could be whatever, it doesn't matter. We all agree that meters is here is what's defining this. So at the end of this, there's a mountain peak on both models. Now,
Right.
due to the elevation change of the star, based on what they're saying, the observer rotating away from it and the Earth curvature creating that elevation drop, they predict that the elevation of their intersection is going to be sooner. So they
Right.
should. So when we subtract at the time of occlusion, when we subtract true position of peak from true position observer, we should not get the full central angle. You would only get the full central angle if the Earth is flat.
Yeah, exactly. Yo. Right. So, okay. The half central angle would be the what, 13 something? Oh, yeah, it is right there. That's what oh, that's a geoterrestrial drop right there. Boom.
Yep. Yeah, the half central angle is just the drop over distance of any arc length on the in their coordinate system.
Right. So the 13 arc minutes would be from where the observer is to the middle of that angle, right? So that would be like halfway between you and the peak.
Yep.
Got it. Halfway between you and the peak. Boom. Which is so weird because that's exactly what they're off by in terms of refraction. They use, it's like something like that, isn't it?
Dude, that's what I noticed the other day because every
Dude,
central
it's look
every
1242.
half
What the heck?
gamma, like it's always within like an arc minute or so. There's a couple where it's a little different. So like they give 17 here when they have 9 for a drop. Like it's
That's
always the
so
most
close, dude.
dude. And so keep in mind this is adding this is like this refraction amount is what gives physical meaning to the ground position in their coordinate system, because otherwise they have no connection to the 15 degree per hour position in terms of
In their
like where
conceptual model.
in terms
Yeah.
of like where it is angularly. Yeah.
Yeah. Earth rotating goes bye-bye.
So yeah, they're always like hella overcompensating for it, which is another thing that Mike noticed. And then like when it gets to these crazy ones where it's like 18 arc minutes and then the central angle here is 22, like they basically are saying that there's no drop over distance
That's crazy. Wait, wait,
for
wait.
all.
Go back to that one. I
Okay.
gotta see that one real quick. What is that? Cheyenne Mountain?
Yeah, Cheyenne.
Okay.
So it's like they say that there's this all this refraction, but when we subtract the difference in position from the time of occlusion, from a true position at the peak, from true position in observer, we get the full central angle. Uh-oh.
That's relatively close, though. That's so hard to tell in terms of
What?
like distinguishable. Like, oh no, no, it's not. Gee, predicted time. Yeah. Okay.
Yeah, no, they're off by 16 arc minutes. I'm saying I'm saying within like how they're, they predict that instead of traversing uh this is like if you subtract this from the 27 or from the 22, this is what it should this is what their central angle should have been for their occlusion essentially, for how much earlier it should have been, which would have been which would have, so it takes 2 minutes 38 seconds to traverse 22 arc minutes. It would have occluded at 1 minute 55 seconds of that transit, or of that angular
I
descent
got what you're
rather.
saying. I got what you're saying. So
Yeah.
between you, the observer, and the mountain peak, the star should have took from you to the mountain peak 2 minutes and 38 seconds to traverse the sky. And then when it was occluded, was actually occluded as it traversed the sky at 1 minute 55 seconds. That's when it actually was occluded. So then
That's when it would have been
Theirs,
included on the globe
th-
at the 1
right?
minute mark, or 1 minute
That's their
55.
that's what it should have been for the globe. Okay, I got it. I got what you're saying. And then for us, is there one for us? No,
Yeah, up
there's
here.
one. Oh, right there.
Yeah, so if their coordinate system following the 15 degree per hour thing checked out, we would have occluded at uh 37 more seconds. So it would have taken
Okay,
37
gotcha.
more seconds, but it didn't. It took the exact amount of that central angle, and then it was over. So there's a 5 arc minute difference, which translates to 37 real second differences. But the occlusion happened at this time because, like we say, there's only one time, right? There's only one occlusion time,
Right.
and
That's
at this time, it happened to be at the end of the central angle where there's a mountain with a rise over run of 1 degree and
oh,
five
that's what
arc
the frick
minutes.
you've been saying, dude. Okay, I got it. There's always a mountain at the end of that angle. I
Yeah.
got what you're saying now.
Yep.
Okay, I got it. It's in there. It's locked in.
Nice, nice. And so yeah, this refraction thing, like Shane was saying about the ground positions, this is what binds the usefulness to the to that true position in their coordinate system moving at 15 degrees per hour. You know, in terms of angular descent rather than motion away from you and when it's going to return, etc. So,
Right.
and then
Sorry,
like
I'm
you were,
coughing for a second.
now you're good. And earlier you were saying how they have expansion series, etc. to account for this. Well, that's how they came up
That's
with
locked in.
the yeah, that's how they came up with the quadratic thing, like correction angles to put into it to multiply it by to give to give whatever needs to be at that angle to follow the 15 degree per hour for the ground position. So it's like literally a curve fit formula. So like the coefficients that they use are derived from that expansion series stuff.
So they can't change it.
Absolutely, yeah. So one, they can't change it, and two, it's not anything that's ever been physically measured. It's what it absolutely 100% has to be to give physical meaning to a ground position to us in their coordinate system for their fictitious observer.
Wild, dude.
Anything else, then it's going to give a different. Then you're going to have a different true position, and it's not going to have the correct ground position for them. So
Yeah, it's not gonna jive with
this
reality because there's only one occlusion time. I got it. Yeah,
yep, yeah,
that's crazy, dude.
yeah. So it would be really interesting. We really need to see measurements in the south because I think that's where we're going to see crazy discrepancies in the angular separation at the time of occlusion.
Right, Alan, do me a favor.
So
Put yourself in their shoes. How could you make a counter argument?
I mean, fully understanding the scope of the central angle thing, there isn't one, and that's why Mike became a flat earther. After just a couple of measurements, he was like, "Oh, yeah, there's the only thing that's at the end of this central angle is a mountain, so I guess it's flat." Like there isn't one, dude.
That's so wild. Well, that makes sense why you've been hearing their arguments, which is non-arguments. They'll never address this.
Nope.
Wow.
Good Tuesday, guys. Ah, it's another day. Nice. Dude, that is nuts, though. Like, it actually sunk in today, for sure.
Nice.
I'm
Any
working on it.
Yeah, well, I recorded this, so if anyone has any questions or whatever that they want to add, it'd be useful for other people to hear answers to or whatever. And Shane, I see you're there if you
Oh,
want
Shane's
to
in
if you
here.
want to talk about your new profound realization of the ground position situation. I think it would be good to add to it.
He's running back to his mic. Give him a second. He was just making food. I was hoping that was true, and he would just come back and be like, "Ha, you got me."
Yeah, I liked it. Especially hat tip there to BC Cleese for asking questions and saying things that help me understand it a little better.
Yes, sir. I mean, that's the only way for me to understand, honestly. Alan's my
You-
chat GPT for Theo, so
So even if we go to Jesse's measurements, where he went to go, find out where the coordinate system would match perfectly, or match perfectly where the flat Earth and globe
I get
intersect,
that
or whatever
now.
for the things. So he went there, right? But then they're 25 arc minutes off. We're 14 arc minutes off. But the time that the star emerged was when it completed its full central angle. If we subtract the time of emergence true position versus minus the true position in their coordinate system for the observer, the full central angle was traversed before the star actually emerged. So its true position had to uh
Oh, because he
overcome.
did an emergence. Oh,
Right.
dude.
So if you were using this refracted position, it would have already emerged
It
like
would already been seen.
right. It would have already been over it.
Oh, I get it now.
Exactly. And then so 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 at the time of emergence, if we subtracted, if the Earth were a globe, if we subtracted the difference here, we wouldn't get the full central angle.
Dude, I
So
totally forgot that that was an emergent star. You should
yeah,
definitely specify that from
I
now
I
on when you talk about
I,
Jesse's.
I do.
It just blew, like, it blows right over my head. I keep forgetting that that is actually an emergence. Oh my goodness, that's what. Okay, yeah. So you would be able to see the star way earlier based off of that, because
Look at
that
how.
refraction doesn't change, right? That's stuck. That's a curve fit formula. That is hard hard factored in there, no matter what. So that means, by their logic, that the refracted star should have been seen way earlier.
Yes, sir.
Oh, got it.
Which would give a different angular separation for the central angle comparison over that distance, and it would be good evidence for globe lads. It would literally
It
imply
would
that the
be
Earth is
good
a globe.
evidence.
It wouldn't be
It
good
would.
evidence. It would literally imply the Earth is a globe, or not. It would be, it would just be that it would be
It would be hard
literally
evidence.
as straightforward as it is for us to say it. It would be, if they had their timings, it would be their evidence. Like, this would be the most profound globe proof that ever existed.
Yeah, especially if you had that emergence and it did show earlier, right? Earlier in terms of, like, earlier than the true position time, then that would, that would be good evidence for the reason why they use that curve fit formula, which is good evidence that it does lift things up, because if the
Yes.
light source is coming towards you, and if it's hitting, yeah, it would bend up. It would be going over, so that means you'd be able to see it over the mountain from the observer on the other side of the mountain.
Yep. And then, like, take a look at this for Houndstooth, where the distance was only 8,700 meters, which is like, what was it, 5.4 miles or something like that. Not a lot of distance,
It is relatively close comparatively, yeah.
and the angle is 10 degrees to the mountain peak this time for the rise over run. And this was also an emergence. It's 3 seconds intersection difference between what we predicted, 5 seconds off, 5 arc minutes. Sorry, arc minutes off of what the globe predicted. Arc minutes for us as well, for 3 arc minutes. But anyway, even here, the star didn't emerge until the rise over run to the peak, because the central angle drop here from true position to observer in their coordinate system is the exact same as the full angular drop to the peak, which at the other end of that distance is 10 degrees 41 arc minutes.
Wild. So they should have seen it. What is it?
6 seconds
Nine
earlier.
seconds? No, wait, 6 seconds?
Six real seconds.
Oh, 6 real seconds. Yeah.
Oh, I'm
Okay,
sorry.
so
That's using
six.
I'm sorry. That's using the refracted position. They should have seen it 32 seconds earlier.
Yeah, 32 seconds earlier they should have seen it. Okay, and put that in perspective, 4 seconds is 1 arc minute, just about, give or take, right?
Yes.
So that would be an 8 arc minute difference. No, no. If FE predicted time 19, so they were off by 2 arc minutes, which is basically 8 seconds. So imagine counting 8 seconds. You should have seen the star already. 1, 2, 3, 4, 5, 6, 7, 8. Doesn't sound like that long until you count it, and you're like, okay. Especially with the refraction built in there, should have lifted it over the mountain.
Yeah, even
That was an emergence, right?
yeah, that one was an emergence.
Yep.
And check out this one for Goose. So he did 16,000 meters at 4 degrees, and the angular separation here was 4 arc minutes for us, 9 arc minutes for them, but the full angular drop was traversed here. So 8 arc minutes, 0.59, that's basically 9, and then so 9 arc minutes. It's just a rounding thing. But yeah, the full central angle was traversed here, or angularly dropped rather. I keep saying traversed. It's not that
I
it
know,
is it is traversing in a sense, but it's better to say the angular descent. But anyway, the at the time of occlusion, 4 degrees 51 arc minutes was 52 arc minutes essentially was a mountain peak. So every single measurement is like that. Not a single one of them is off.
Oh, dude, this is so edifying.
So like remember all the contentions for Green Mountain, or I'm sorry,
I
North Peak.
do.
Yeah, Green Mountain and North Peak, where Jesse and like in Jesse's analysis using the thing and the angular size of the lens and all that, like I don't disagree with the optics of it, but at the time of occlusion, the full central angle was traversed, and the prediction for a flat Earth is 44 arc minutes for the relative mountain angle, and the angular difference in their coordinate system between true position of peak and observer is the full angular drop again. So whatever it appeared to look like due to whatever optical things were going on, because this is the longest, 130,000 meters.
That distance.
That's like 80 something miles. So this
Right. So
peak, this
you can see that in the time right there where
yeah,
it
this is
says 360 drop, 17, what is that? 17 minutes?
17 minutes. Yeah,
So
it's
17 minutes is traveling the full arc length from the observer to the mountain peak. That's how long the star has, no matter what, based off of that conceptual model, because there's a mountain peak there
yep.
that's intersecting it. Got it. Okay. So, wow, it's so close. I see what you're saying. It's 11 arc minutes, dude. That is so crazy.
Where are you seeing 11 arc minutes?
110 versus 110 42 24 versus 110 31 81. Where you said it travels the whole arc length almost. Like it's literally like you're right. It's like right there.
Oh yeah, the only difference here is arc seconds, which is just rounding errors and stuff.
Dude, so it's like it is. Yeah, exactly. Yeah. That's true.
It's literally the exact arc length.
Crazy. It makes so much sense why the oh my god. It just hit me, dude. Like really hit me. Why longer distance observations would be such a significant difference between models. Because the longer the distance, not only is there more drop over distance, but the sky should be rotated beneath your like it should be rotating way out of your field of view. If you think about it, logically speaking,
Well,
you're farther
it's
away.
just as you're rotating, that elevation difference is what's causing the star to drop, over that arc length.
Right, but think about it like this: the farther away you are, right, the more uh if you think about the
Oh, the more angular separation there's going to be between the true position of the star and the
and the
observer,
mountain
because
peak.
there's more time for it to deviate, like more angular separation. That's true. This is the biggest, like 1 degree and 10 arc minutes is the largest central angle that we've done, and this is one of the largest discrepancies that's produced in it.
Yeah,
So,
dude, the discrepancy comes from their conception of it rotating too, like that's what's causing the declination,
well, the
right?
rotation is just kinematics, because you could have a stationary globe in the sky rotating, but it's just easier to conceptualize it as you being on the sphere and or whatever, so because that's what we've all been taught. But so the rotation part isn't the significant part. The significant part is that over that, like the arc length has a curvature to it, that half gamma, which is why the star is dropping because the Earth's a ball. That would be what that would be what they're saying.
Right. They're
So
saying that there's an arc length because of curvature of the ground.
yeah, so the more
Um,
distance of no curvature, there's going to be more angular difference between true position and reality versus what their coordinate system predicts. But look at the time of occlusion, 241 hit the full arc length, and the rise over run to the peak is 144 or 044 there.
Yeah, it's still the curvature is the elephant in the room. It's not the motion of the Earth or a stationary globe with the stars moving either way. Right. It's the elephant in the room is still the curvature, not the motion. Like you said, it's kinematics.
Yeah, because the
well,
rotation is just 15 degrees per hour.
Right.
what he's saying though, look, so okay, I'm starting to understand these numbers a little bit more now. So the star peak true, 58 arc minutes. Boom. Okay. That's the actual true position of the star based off of 15 degrees per hour, right? Relative
Yep.
to
Yep.
where you right.
Yep. Relative to the observer. Yep.
Okay, relative to the observer. Boom. Okay. The actual occlusion time for FE versus rise over run, um, where is it? Right there. 44.29.
Hmm.
So the minus 14 is how far flat Earth was off in terms of the occlusion time with the rise over run. But for them, they haven't even went the whole they still haven't went the whole arc length, right?
Yeah, it's how far we're off in their coordinate system. So
It, that
so
one
but
10 though is what I'm saying. That celestial drop right there,
yes.
right?
Yes.
Their true intersection should be 21 arc minutes.
Yeah. Yeah, you should subtract 21 from this 1 degree 10 arc minutes.
Wait,
So this, like, their central angle at the time of occlusion, if the Earth were a globe, when we subtract true position from peak and true position to observer, it should be like, to make it match up for the globe, but you would take their intersection difference and subtract it from the central angle, because that would have been the time, that would have been their ideal intersection, the same way that we hit our ideal intersection at the end of the central angle.
what would that be actually? So 110 minus 21, right? That's the
Yeah,
numbers we're using. Wouldn't that
I'll set
be the
I'll set
true
it.
position?
I'll set it. Hang on.
Isn't that
I'll,
isn't that just
no,
the same as the true position? The star
for
true
us,
position?
it is.
Well, for the model, I'm saying.
It would be where the true position would be at the time of occlusion. Yes. So yeah. Oh yeah, yeah. So it would have been, it would have just been the geometric.
58.
It would have been the geometric prediction here. I bet. Watch this. Give me 1 second.
Okay, I got you. Sorry, I'm all excited.
So they would have predicted an intersection at 49 arc minutes of their central angle of that full central angle. That's what it would have included for them.
Gotcha. Oh, that's a good number. Okay, so in terms of, okay, I see what you're saying. 4920. Oh yeah. Oh, right there. Where you have geo globe peak predicted 9 arc minutes.
Yep.
Add 9 arc minutes to that. That's your true position.
Yep.
Oh, got it. I feel like Zach Galifianakis in The Hangover right now with that meme. We're just looking at all the math.
Yeah.
Like I'm
Yeah,
just.
because this is basically oh wait, that's 0.59, never mind. So yeah. No, you nailed it.
Okay, I'm just
Yeah.
digesting it in my brain, guys. Sorry if I'm talking out or thinking out loud. Well, good on you, Alan, and Brian, and Mike, for
Yeah.
freaking
And Shane, dude,
and
everyone,
Piezo. Yep.
Sam, dude, everyone's been putting in work.
Yeah, man, this is.
Well, not everyone. Some of us are just learning.
No, that's
put in
totally
work.
fine. Yeah, that's literally also work.
Yeah, if you know how to argue this, then you can also spread the gospel of the spreadsheets. No, but this is, in all sincerity, this is crazy, dude. They're stuck.
I just like I said, I just kind of fleshed this out recently, but it was like once I got it, I was like, oh, these numbers, like if we subtract these two at the time of occlusions, for a globe for earlier, they shouldn't get the full thing. Shouldn't, like, that's GG, dude. Is the only thing that's at the end of there. It's a mountain with a relative rise over run of 144. If the Earth's not a globe, this is the only thing that's there. Otherwise, we would have had to wait for the refracted position to do its time. So we would have had to wait another 38 seconds before it got occluded.
Tell me if I'm wrong, but it seems like what I'm hearing, um, you're talking about when that star should occlude if they get their full central angle, right?
Um, they would never predict that they get the full central angle because their occlusion's earlier. So so that's what this column right here that I just made is, which I'll formalize it later and give some numbers to it, or names to it and whatnot. But the important part here is that their central angle, so the distance and angular drop, converted over this distance, is 1 degree, 10 arc minutes. So because they think Earth's a ball and it's curved and all that, the geometric alignment for their 15 degree per hour angular descent over this arc length is, it's going to intersect with the mountain peak at 9 arc minutes, when it's at 9 arc minutes above the horizon, which would mean that the star was only able to angularly drop 49 arc minutes of the 1 degree and 10 arc minute distance.
Yep.
Or
Okay, I got you.
over that distance, I mean.
Before it got occluded, way
Right, it would have got occluded way sooner. This is what
sooner.
would create the timing difference. So it would have got occluded 5 minutes and 7 seconds early. And then in their coordinate system, we would have occluded later by 3 minutes and 26 seconds. But again, that's just referencing the angular difference between reality and their internally consistent system. But at the end of that arc length there, we traverse the full amount, and the relative mountain elevation is 144.
44. Right.
Oh, sorry, yeah, 44. I threw an extra 1 in there for good measure.
You did it twice. I was like, I got it. I got to say something.
Yeah, thank you.
Okay, so real quick, what you're showing in FE predicted 44. That's just the difference between what was the actual occlusion time. What was the actual occlusion time?
21/11/40.
21/11/40. And then that would be actually at, so, and that was at 58 arc minutes. So that's the, like, that's what equals that. So 21/11/40 gives you the true position of the star at 58, correct? 58:43.
Yes, sir.
Right. And then FE predicted, boom, 44:29, and that's just based off of rise over run from the distance.
And that run, right? That distance
That
is
run is
the
the arc length
is the
equivalent.
arc length. Yeah.
Got it.
Yes, sir.
Wild.
Man, we spent the first 7 months or so sticking a knife in, and now you're just twisting it.
No, it's crazy. Actually, there's a lot of implications that I don't want to say yet, but I'm digesting them right now.
So this is not only evidence of no curvature, but no motion, right?
No, motion could go
Would
either
say no
way.
motion.
Yeah, this wouldn't be able to determine motion because if the Earth were station, well, yeah. So because it implies that the Earth isn't a globe, the alternative would be a stationary Earth. But I guess you could have a rotating Earth with a stationary sky. So I guess no. But no, yeah, just
No,
based
no,
off,
no.
yeah, just based off of this alone, if the Earth were
Well,
like
I mean,
were
based
stationary,
on based on a globe, um, you can eliminate the curve, but you would still need that motion with that curve. I mean, that's the idea. They need the motion and the curve. If they can't have one, then they can't have the other, right?
no, they absolutely could. The motion could go either way on either model. It's not dependent.
Oh, like
The
it
sky's
could,
moving.
we could
The
still
sky's
be
moving.
rotating.
Yeah, yeah, yeah.
All right. I get that.
Or stationary.
But because of the way that the measurements turned out, not showing that the Earth is a globe, then they lose curvature, which we would take the stationary Earth position. But hypothetically, right? I suppose you could say that the Earth, the stationary, like laid out like a Gleason's, like we're all familiar with, would be rotating and the sky would be stationary, and the angular difference based off of your perspective would, that the effect would still be created. You know what I'm saying? So like the motion's independent
Yeah,
of that.
it's kinematic equivalent. So yeah, it's not really mutually exclusive. But dude, the stars going beneath your feet, man.
That's game. Yeah, that's now out of the question.
GG.
Yeah, that's conclusively out of the question.
I know what you mean, Kembo. I totally get what you like. Yes, but the thing is, in terms of argument's sake, motion is not the same as shape.
Yeah, you're right. But I mean, logically speaking, if you eliminate curvature, motion, I don't know. I don't know. To me, motion just seems. Why are you even asking if you're moving if you're flat?
It's just
Well,
not the
that
argument. No, I
that
agree. It's
is
just
the
not the
obvious
argument.
implication, but it's just not the significant part.
But I get where Kembo's coming from because you still think of it in their conceptual model as a whole. Earth rotating, stars declining or going out of your field of view. Out of your field of view to them is beneath your feet. You know what I mean? So like that whole thing needs to be rectified.
I
Oh,
mean,
dude, that's
it'd be going beneath your feet if the Earth was a globe and the stars were moving as well, right?
Yeah, but if they linger at the end, um, doesn't that kind of take 15 degrees per hour rate?
No, that's the
what
beauty of this. There is no lingering for the true position. The
right.
intersection, like only the apparent position lingers. The actual true position elevation is what's not really changing. In the way that they need it to angularly. That's why these differences come up, because the star's true position didn't actually angularly change following a descent relative to the observer of 15 degrees per hour to create that alignment. But it did, however, move at 15 degrees per hour relative to the observer to cross that. I'm going to say it again,
Central angle.
to traverse that central angle, which is the distance, in Earth, of the arc length of that distance between the observer and the peak. So which over that time would create an angular separation of 1 degree and 10 arc minutes.
Now,
So
is that central angle tied into the fictitious observer?
Yeah.
yes, it is. Yes, it is the back. It is 100% the backbone of what relates a ground position to a star. Like it's how they merge the celestial and terrestrial sphere model. So, if I got this image up here, if you take a look at this, they would say, hey, we're an observer up here standing on the top of this ball, but to make stars move in reference in accordance to 15 degrees per hour, 60 nautical miles per degree, to have this linear portion to make this coordinate system make sense, we actually need to transform to the center here and then
So
put
we
the
need to.
star
Uh,
up here and then have it follow 15 degrees per hour. And by doing that, we've now merged the celestial sphere to the terrestrial sphere. So now the star has a ground
360.
position for
Right.
24 hours of day, regardless of whether or not you can see it or whether or not it's actually at that position angularly. Its true position is now tied to that for the purposes of the coordinate system, and its apparent position will now be referenced as the deviation from that.
Yep. And check it out, right? Check it out. 15 degrees per hour, 1,000 miles per hour, 24,000 miles in circumference. You see what I'm saying? That 15 degrees per hour,
Yep,
that's what they're stuck with.
Yeah, all right here in the sky clock section. Nailed it.
You know, so like they have to put the fictitious observer at the center of the Earth because in their conception, but the ball Earth is 3959. That's the radius, right? So then the central angle from the center of the Earth to the middle of that arc length is the central angle, right? And that central angle is basically what they're using in terms of the reference of the true position of the star. So if you were to take the middle of that triangle, shoot it up into the sky, that's the true position. Well, guess what? The true position is now referenced based off of where the mountain peak is. You see what I'm saying? Like,
yeah, we're no
so
longer in the center. We're now utilizing the mountain peak.
yeah, and the entire arc. This is what Alan is saying, where
Well,
they have to travel the whole arc length, but the arc length, that's where the mountain peak is.
So
Right.
you so yeah, when we go to the mountain peak and we do another reference check at the center of the Earth there, and we see that the star's angle relative to that at that time is the same as it was for the observer when it started the angular descent from 2 degrees and 33 arc minutes in their coordinate system.
Like saying traverse. You could say traverse.
Angular descent needs to be embedded.
I know.
Angular
I know.
descent over the arc length.
Right. Yep. So
It's actually like a
beginning of that.
beautiful system how they came up with this and merged it together. It's really cool, but it has no physical meaning, unfortunately.
Yeah, it's just utility. And they make the pragmatic fallacy where just because it's useful doesn't, they think it's true in their mind. that means we're on that. So we're on, guys, because it works. Wild. They literally took the sky and said that sky means that we're also on a ball. That's so nuts, dude.
Yeah, if you take any of these occlusion angles.
Oh,
or
shit.
ti-
I wasn't
Yeah.
talking this whole time, son of a bitch.
Dude, this whole
No,
time
we've
I've
been
been
waiting for you.
I was like, you guys not listening to me?
Yeah, dude.
All right,
Yeah,
I was
dude. We're just
mostly-
yeah, dude. We're just purposely ignoring you as a prank.
Like, well, you just did it now, and I was like, Al wouldn't do that. Something's wrong. I was like, what's going on? Fuck.
Did you
How
hear
how
me
much
try
of
to
how much of
be
this
like,
did
yo,
you
he was
catch, man?
eating?
Well, so the
Yeah.
ground position, dude. So not only that, but that they physically manifested a new geographic position for every theoretical star that could exist all the way through the model. That's what they do with that.
Yeah.
So it's like super. So like, hey, can you measure one zenith one time? Well, guess what? All the stars that exist in Ursa globe. We've completed our model of the mimic of the sky with the theoretical sphere under another theoretical sphere, and now we merge them together, and now that's the world. Dude, remember before I was like, I'm gonna be a WGS 84 Earther. Like, I don't even want to argue against this because this so airtight and it's so like close and accurate and reliable, and like astro geodesies confirm, like, when satellites confirm it down to the millimeter and whatever, like they obviously have their shit internally consistent and down, and like, you're not gonna say you're not gonna use it. So it really is the beautiful understanding is how little the surface of Earth has to curve in all of these models. It's zero. It's zero, dude.
And in
So
fact,
true.
zero of it does curve. Otherwise, these occlusions
So, like,
would match
Otherwise,
different
it would-
central
The
angles.
truth is, it's flat, and they made a ball model, and it doesn't matter. That's the truth of it. They made a ball model, and it works so well that it doesn't matter, even though the Earth is definitely flat.
the
Dude,
truth
but-
is they couldn't make a ball model without it being flat in the first place, dude. That is
don't
the
know.
crazy part.
Maybe
Yeah.
I don't know what a real ball would look like. It seems so crazy.
No, I'm saying
mean,
the
I feel like
elevation
if
angles.
I feel like if their conditions were as told to us, it would geometrically work out. But in any case, Shane, did you catch my new argument on, or like my new breakdown on the central angle and all that?
Yeah. Yeah,
Nice.
but that's what you've been saying the whole time, though. You just made it more clear.
No, but I just realized like the significance of this part of it, which
Yeah.
makes it even more damning because the only thing at the end of this distance is a mountain, so, and it's our mountain.
Yep.
Like their time
Yep.
was early. Like I don't know. It really dawned on me, especially when you said, or when you brought up the ground position situation when we talked about that the other day. It's been marinating.
You gotta call
in
it
my-
geographic, I think. I don't think it's not even called ground. We all just call it ground, and that solidifies it. And we were all fearful of it for like 3 years. We all assumed it was real. We were like, well, it must be real. It's not even called ground. It's called geographic, literally defined by the coordinate system anyway.
Well, okay, so anyway, the geographic position, like why that's off in angular separation there is because, like, the star isn't actually angularly descending, which is what it needs to be doing to give physical meaning to their geographic position in their coordinate system.
Yep.
So yeah, it was just really crazy that if it was descending in accordance with their coordinate system, it would take another 11 seconds or whatever, but it didn't. It traversed the full central angle, so like the distance is consistent with their model, right? But the
Which can be our model, I think we're saying.
right, but the angular descent of the star is arbitrarily fixed to 15 degrees per hour at a descent rate relative to the observer to make it to give that fictitious, or to give meaning to that fictitious observer that's referencing it, because that's why all the refraction corrections have to tie exactly back to
Hardwired. Yeah.
where its true position is to give meaning to it for that fictitious observer.
To make
Yeah.
the fact that the fictitious observer is not where they say.
Yeah. So they just made up another one and then used it for the whole model, and they were like, boom, now now everything has a real position. And go fuck yourself, flat earthers. That's really what they did.
Yeah. Well played, guys. It was a good one.
Yeah. you got me for a while because I thought that I kept on I understood them as what geo put like a physical spot in the ground, and that's not even what it is. That's not what it is because they haven't done that. And all they did was calculate it based on one reference epoch and go take a zenith, and they chose that, and then boom, spun it all around, and then just said, "Listen, you see how this is a zenith here? Well, if we wait a while, there'll be another zenith over there, and we can calculate how long it'll be until that star gets over here." And that's what they do. And they go, "Now we have all the stars."
Yeah,
Boom.
it's like a process of like a matching game, right? You have a whole bunch of stars, and it's just like, here's some real positions. Okay, from here, then it
Well,
has to be here.
they take one and then they calculate everything.
The first point of Aries for that epoch or whatever. But they do have nautical almanacs though for navigational stars, right? Where they
Yeah,
tie
but
it to pragmatism. I'm
no,
just
nope,
saying with celestial
nope.
navigation.
You know what that reference is? The geographic position only. That's what it only gives you. You only ever get the geographic coordinate reference, nothing on Earth. I mean, it's tied to the graticule. Dude, the way that it works, it's like 3 to 4 layers of abstraction layers. It goes through like a typical navigational abstraction when you take a bearing of a star to go in that direction to getting a 3-star fix, meaning that you're now putting a theoretical ground position in a circle and you're doing circles of equal altitude around that one. So now it's kind of a real thing, but still not really. Still, you'll never get to it. And then later they were like, "Oh, you know what we can do? We built our model. We're gonna make intersection points." And now they have once they have geographic positions and they're defined in the coordinate system, then they made them real. But they only exist when they merged the models and created them.
Are those called conjunctions?
What do you mean?
Like if you
Merging the
reference the
two
almanac,
models?
though, the almanac will only give you the time of the GP, so the geographic within the coordinate system based on the time. That's all it's going to give you, and that's all. That's all the almanac ever references.
Which is
It
the true
references their own
position?
made up, their
Yeah.
own made up, exactly their own made up, like calculated position of where they think everything should be.
Yeah. All right. Well, I think that wraps up everything I wanted to bring up and discuss for this. If there are no further questions, I'm going to go ahead and end the recording.
Great Prezi, bro. Very
Oh, you were
edifying.
recording? I thought we were just showing.
No, I was recording that.
Both.
But also both.